And okay, I'll start. So I'll just explain the maybe the topic a little bit. So what we're really talking about is like rational points on curves. So maybe like for example, if you take, can someone like give me a really simple example of a curve in like two-dimensional plane? Some simple example.
Hyperbolic curve.
Okay, even simpler example like some conic section maybe.
Circle, ellipse.
Yeah. Okay. So circle would give away too much. So I'll maybe is it fine like if I talk about parabola? So because it's really simple to visualize it and uh, talk about rational points on it. So basically, so for example, if you have y is equal to x squared, and if you draw it in the real plane, you know that all the points are real numbers, right? So basically, what I mean by real point is that both the coordinates, x and y coordinates, are real numbers. So it's really simple to think about these curves in terms of real numbers, but when we have to find rational points on it, and rational points, by rational points I obviously mean both x and y coordinates are rational numbers. So that is a more difficult problem. So for example, in the case of y is equal to x squared, can you give me a rational point? Uh, okay, Biona raised hand.
1, 1.
Yes. So that is a really simple. That is really simple to find, right? If we just substitute into x some rational point, then we know that y would also be rational due to the property of real numbers. But but this was an easy case. For example, someone mentioned a circle, and in a circle, it's more difficult to find a, rational point. So that's what we're going to be talking about today. Okay. So I just took a jump. So uh, suddenly from curves, you're on elliptic curve because I want to like uh, in the end introduce elliptic curves. So this is just like a motivation for studying elliptic curves. So why study elliptic curves? So basically, there are two main reasons which we should be able to understand right now. The first is that it is intimately connected to number theory. So if you want to solve some number theoretical problem, there's a good chance that it might be related to elliptic curve. And the second is that it has, and this is something that is really weird, it has applications as well, and applications in cryptography. So has anyone heard of cryptography? Can someone uh, like talk about what it is actually is? Okay, so that's fine. So cryptography is basically about codes. We're trying to like encode messages, and we're also trying to break them. So it turns out that cryptographers really use this method of they pick some really large prime numbers and they multiply them together, and somehow the message that they're sending is encoded using that really big composite number. And elliptic curves provide us with some algorithms to factorize these. And if you are able to factorize this number, you are able to decode the message in some sense. Uh, and Lenstra's elliptic curve algorithm does that. Yes, you know.
What are elliptic curves? Are there only ellipses and circles? Or hyperbolas
Okay.
are also allowed?
Uh, okay. Okay. Elliptic curves are not definitely not ellipses. But yeah, that is a like a very common question and a good question. But no, they're not ellipses. They're not circles. They're not related to conic sections even at all. Uh, the Okay, I'll maybe when I get to elliptic curves, I'll explain why they're called elliptic curves. Uh, Not right now. Yes, Ishan.
Yeah, is it possible at present to give some idea of what these curves are? I mean, maybe not a full definition if we can't understand the terms, but still to get some idea?
Yeah, I'll be getting to that. This is just like a motivation thing. Okay, so elliptic curves are like cubic curves. Okay, and they are smooth everywhere. Mm, like smooth as in they have no sharp edges or sharp points. Uh, I'll be giving the definition in a short while. Is that fine?
Yeah, okay,
Okay.
thank you. Thank you.
Mm. So play a big role in photography and help us solve problems in numbers. So this is just some history for motivation. So Fermat's last theorem, I suppose most of you would have heard of it. So it's basically about solving this Diophantine equation, like x raised power n plus y raised power n is equal to z raised power n, and x, y, z are all integer numbers, and we are trying to find non-trivial solutions. So some obvious solution like 0, 1, 0, that we are not going to be we're not interested in that. We're not interested in trivial solution. So n is greater than equal to 3. But the case of n is equal to 2, the answer is clear that there are solutions. But for n greater than equal to 3, there are no solutions. This is a theorem. This was proved by Andrew Wiles, and the proof was given in this journal. And I'm basically trying to because we're interested in number theory, like I am interested in number theory. So I'm just giving like the connection. So there's this modularity theorem. Like I don't even understand what that really is, but it turns out that this modularity theorem, which is for elliptic curves, it is intimately related to the Fermat's last theorem. And if you could prove this for some specific type of elliptic curve, it would imply the Fermat's last theorem is true. So uh, and this is like it was proved by Ken Ribbett. Many mathematicians had a lot to do with it, but uh, Ken Ribbett proved the relation between proved the connection between Tanya Mashimura and elliptic curves, and that it would imply the Fermat's last theorem. And this is precisely what Andrew Wiles did. He uh, proved this modularity theorem for some special elliptic curves, and it applied Fermat's last theorem. So the actual proof had very little, you can say, to do with what we think number theory is. Okay, so now we get to the mathematical part. So does anyone know how to how we can find rational solutions of this polynomial? So suppose that p of x is equal to 0. How can we find rational solution? Uh, so all the coefficients are rational numbers, and we just have to find a rational x such that it satisfies it.
Oh,
Yes.
Yeah, Kathy, go
Okay.
ahead.
yeah, so I think if we can test using rational root theorem.
Yes. Exactly. So basically, rational root theorem states that if there is a rational root p by q with p and q relatively prime, then p divides a naught and q divides a n. And okay, so there is a mistake here. Uh, what uh, what we have to do first is that because it's equal to 0, we can multiply this by a really big number such that all the denominators of the coefficients cancel out because we took them to be rational. So we first convert them all to integer coefficients, and when we have integer coefficients, we can apply the rational root theorem to find the roots. And multiplying by a non-zero number wouldn't really change the nature of non-zero integer wouldn't really change the nature of roots. So this is really easy, right? Even though in practice it might be really difficult to. So for example, if the coefficients are really big, you would have a lot of possibilities. But since the numbers are finite, we know there would be a finite number of divisors. Therefore, there would be a finite number of possible rational roots, and we can test all of them, and we can eventually find maybe some rational roots. So is this clear? Okay.
So can you go
So
back? Let us see how we'll ask few questions. So how do you show that P is a divisor of A naught, someone? Yeah, Keshav, go ahead.
Yeah, sir. So basically, we just substitute some rational number, right? So if we substitute, then we know the GCD, they are relatively prime. So say if we substitute P by Q and then take Q or the right, then we will get an equation involving P and Q. And since P like does not last term will have only coefficient of Q, so P will divide A naught. P must divide A naught, and similarly Q must divide AN.
okay. So Acha, you were asking for a proof, sir.
Just I'm asking for a proof.
Okay,
So
okay.
how many people will say about?
So is everyone? I'm not able to see like hand raised.
Yeah, it's okay. Are you able to see raise hand at least?
I have to like tap on the mobile phone to see
Okay.
that.
Uh-huh. So I don't know, but there is a show participants is there, na? There is a in the panel there is a thing called show participants, right?
Yes. Okay.
So that you need to click. Yeah.
Okay.
Now your photograph is reversed actually. Now you are in tilted.
Ah. uh, but it's on auto rotate. I don't know why. Okay. So
Okay.
I'll just tap the thing when
Yeah.
necessary.
Yeah. Okay.
So does anyone have a problem with the proof?
Ishan, yeah, you want to say something? Please go ahead.
No, sir, you had asked if we had understood the proof, so I just
Right.
that's why I.
Yeah. Right. Okay.
Okay. So I'm okay. I'll go ahead. So this was polynomials in just one variable. Suppose you have, and now we're talking about polynomials in two variables. So, but since otherwise it would be too general and too difficult to talk about it, so we'll just go degree by degree. So suppose you have an equation that looks like this, and again this is a rational, this is a rational equation. So A, B, C are all rational numbers. So how can we find the rational solutions of this equation? Uh, if anyone wants to answer. Is the question clear?
Um, can I ask something? Sorry, I should have raised my hand. Sorry.
No, no.
See, no
Uh,
need to raise hand. Actually, number of participants are less, so you can speak actually, so that it will go a little
Yeah,
faster. Okay.
yeah.
Yeah. Yeah. So first Ishan, go ahead. Then Viana will ask. Yeah. Go
Sir,
ahead.
I thought again, if you make all the integers yeah, all the coefficients integers, and then there are methods of solving Diophantine equations, so we could use them.
Okay. Uh, we're just asking for like any rational solution if it's possible to find any. So like we can just uh, like substitute some rational number in x, and
Oh,
that would lead to a rational y, right?
yes, that's correct. That's correct.
Yeah. So that's all we have to do. We just have to find some rational solution if possible. Okay. So otherwise, the general case maybe is too difficult, but we're just interested in some rational point, and yeah, they would. It's obviously clear that if there is that you would be able to find infinitely many rational points. Um, although it also depends on what if A, B, C are whether they are zero or not. So yeah.
Viana,
Okay,
you want to
maybe.
say something?
If both of them are non-zero, you can put x is equal to c by a and y is equal to minus 2c by b. And if any one of it is if any one of it is zero, for example, if a is zero, you can put y as minus c by b.
Yes, that is correct. Yeah, my y is equal to minus c by b, since c and b are both rational. Y is rational, and x is obviously can vary because y is constant. So you would get all the rational in.
So before I'll ask one question. So earlier equation polynomial in single variable, and there you completely figured out that what are all rational points, right? Here to get one rational point is easy, as Lalit told. You substitute one rational for x, then y also become rational provided a, b, c are rationals. Fine. So with that you can figure out that. But in general, I want to find all rationals, right? All rational points. So I'm not saying that we'll answer it or like that, but generally, what are the questions one can ask? Finding one rational point first, then finding all rational points, second question. So like that, right? And is it depends upon ABC. So these are all the things we need to look into. Yeah. Okay.
Yeah. So yeah, as Satyasar said, you have to look at the coefficients. It depends on a case by case basis. Sometimes, especially in this. So yeah, and yeah, you just substitute some rational x and solve for y. So we come to the case of two variable polynomials with degree 2, and okay, so can anyone like tell me what like this is actually like interesting, and this is actually a little difficult. So if anyone would be able to tell me how to solve this, I would be really impressed. So if anyone has an idea.
इसमें हम
Maybe you can ask the question case properly. Maybe someone is having Devesh is want to say something, but before that, it is better that you specify the problem, what exactly you are looking for, so that they may start thinking.
Okay, so we just have this rational conic equation of a rational conic. So basically, all the coefficients are rational numbers, and we're looking for rational x and y such that f becomes 0, such that f of x comma y becomes 0.
maybe we can consider it as an quadratic equation in x, then solve for x.
Okay. The problem with that would be that you don't know if so for example, like you take a rational x, some rational x, random rational x, then you don't know if you solve for y if that y would be rational or irrational, because in when you solve when you get the quadratic formula, uh, you get a root, right? So that root could have the discriminant negative maybe. So that would be even worse than an irrational solution. That would be a complex solution. But we are only looking for rational solutions. So that would not. Was someone saying something?
Yeah, I was saying, can if in case b is 0, right, then we can convert into perfect squares. Like then this is just a, a conic with axis is x-axis and y-axis. So it will obviously intersect somewhere, right?
Yeah.
In that case, we have rational solutions. Maybe we have rational solutions.
Intersect with the axis.
Yeah, in case it intersects with axis, it will be solvable using quadratic formula, right?
Okay. So, but it's not necessary that it would intersect, right?
Yeah, it's not necessary actually, but like we can convert into perfect square, then we can solve over p by q.
Okay. Okay. So the answer to this, like, like actually finding the solutions is very difficult. So for example, if you were to try what Devesh said, so if you were to try using the quadratic formula, you have to consider only the cases where the root, the discriminant under the root is actually a square number. So otherwise, it would not give a rational solution. So that is difficult. Like you cannot do it every time, and it depends on the coefficients as well. But an easier way to do it, and this is a more geometrical thing, is this.
Can I ask something? Can I say something?
Yes.
So me, this equation, if you can reduce it to a conic, then I'm just saying maybe it would simplify solving the problem. So if you can reduce it to the equation of an ellipse, then you can maybe there are techniques to solve for rational points on an ellipse.
Okay, that's a good point. But yeah, so you're suggesting that I transform it, right?
Yes, yes, yes. Into an
Okay.
equation which you recognize.
Okay. So suppose you do that. Uh, so you're trying to find the equation of the solution, rational solutions of something that is not reduced, like not transformed, and you're transforming it and then finding the solutions. So would not the solutions change? Like wouldn't x and y, this, if there were solutions in is there solutions in the transformed case, would there also be solutions in the original equation?
I don't know. I don't know.
Yeah. Yeah, so that is actually the problem, but that is a good observation, and I suggest that you try to do it for some example. So maybe it would lead to something. So okay.
So make it more clear what Ishan is saying. Maybe that for example, you take x equal to some again a small a capital X plus small b capital Y is equal to
Yeah.
c capital X plus d capital Y, and you substitute. Then so now a b c d sorry, already a b c d are here. So we will take some other variables p q r s. So now if PQRS again rational, then again you need to think of that way also. Now you are converting the equation to other equation, as Lalit rightly asked. So then again you look at, you find a solution there and you get back the solution here, right? So now while converting into another, you are converting with some transformation. That transformation, what about the variables? All these comes into picture, coefficients, right? Yeah, so that yeah, that is a good observation to look into. Yeah, that's what Lalit also already told. Yeah, proceed then.
Uh, okay, so maybe to speak more on it, you can. Okay, so suppose you have this circle that has a center 2 comma 3 and has radius 1. So it would have the equation x minus 2 whole squared plus y minus 3 whole squared is equal to 1. Uh, so you could just shift it, right? Shift it to the center. That's what you were saying. And so the question is basically, the question basically would be, if you had a rational point on that circle, would that stay preserved? Like, would you
No,
still get a rational?
no, the solution would change, but then can't you shift back to the original solution? Because when
Yeah,
you're
that's what
shifting,
I'm saying.
hmm,
That's what I'm saying. So you're basically saying that if that was a rational solution, would the rationality be preserved in some sense? That whatever
okay.
solution you get after transformation, would it be rational or not? It doesn't need to be same.
Mhm.
It probably wouldn't be.
Yeah,
Uh,
no, I did not think at all about whether it's going to preserve that it's a rational solution or not. So,
yeah.
so I can think about that.
So you can think about that. That's a very good observation. So let us try to understand this with an example. So okay, I'll just because the images were for some reason getting inverted. I'll just okay. So suppose you have we're back to a circle. Okay, so you have the circle with unit radius and center 0, comma 0, and we're trying to find the rational points on this. So can someone give me quickly like a rational point that is obvious to see in this?
10.
Yes. So 10, and you actually have four really obvious points with where the circle intersects with the coordinate axis. So it's going to look something like this, and you have -1, 0. And okay,
Keshav,
so
Keshav, give some 5 points fast. Keshav, give some 5 points.
Yes, sir, I'm thinking for fifth one.
That's the reason I asked 5.
okay, uh, so yeah, 5 would be uh, they would be non-trivial, definitely. So uh, yeah, but otherwise you can see that these three are definitely rational. Uh, so okay, uh, so if you have this point -1, 0, uh, and suppose you put a rational line through it. Okay, so we are working with like some line like y is equal to mx plus c, where m and c are rational numbers. So as you all know, m is the slope and c is the point where the line intersects the y-axis. So suppose you put a line passing through this, then the equation of that line would be this: y is equal to m into x plus 1. And if we stop, so what we're trying to do is we are trying to find the second intersection point. So how can we find the second intersection point uh, of this line with the circle?
This is very nice. So once you've this rational line generate, so once you put in, so if the line is y equal to mx plus 1, so x is you have a rational solution x and y. So you can figure out how y and x will be related on this line, and then you substitute that into the equation of the circle.
Yeah, yeah, that's correct. So
This is
you
exactly
basically
what
need,
you are suggesting also, right? Earlier,
uh,
some type of this sort. You are also looking some
yeah,
transformation. You are now converting y variable, right?
yeah,
Y you are expressing in terms of x. Ishan.
Oh yeah, yes sir. Yes, that's what I was thinking of. I thought you were talking to Lalit. So
No, no, I'm talking to you. Earlier also you suggested something transforming.
yes, yeah,
Look
yes,
at that
that's what I was thinking.
perspective also. Yeah.
Hmm.
yeah, that's a good way to look at it. Uh, so so what we do is we just substitute it and we get the second intersection point. So we get this equation and we just solve for x. And okay, so most of you know this, right? So if we have two for because we would have two solutions for x. So one of the solutions we know x is equal to -1, and we know that the sum of the solutions is going to be related to the coefficients in some way. Can anyone tell what that relation is? The really simple relation.
Yeah, so the sum was minus b by a. I mean, assuming it is ax square plus bx plus c equal to 0.
Yeah,
And the product is c by a.
yeah. So Biona, you don't need to raise the hand. You can speak directly. Uh,
Okay.
okay. Okay. So
I found
yes. Yeah.
something. You can, if you have a Pythagorean triplet and if you divide it by the hypotenuse, that is always a root. For example, if you have 5, 12,
Yeah.
and 13, then 5 by 13 and 12 by 13 always works.
Yeah. That is correct. Yeah. You can. So we're looking at the rational solutions of this. So it's equivalent to look at capital X squared plus capital Y squared is equal to capital Z squared, where X, capital Y, and capital Z are integers. Those two are equivalent case. But there's just one slight problem. So if you consider like capital Z to be 0, uh, then you get some problems. Like if, for example, the powers were different, then if you take capital Z as 0, then you can't divide. So that's just one problem. Uh, Otherwise, it's fine. if you have non-trivial solution, that's fine. You can do that.
Yeah, here I want to ask a few questions. Yeah. So Vienna, you told one point. Can you again suggest that point?
If you have any Pythagorean triplet PQR,
Okay,
then
take
P by R and
let.
Q by R are solutions.
Okay. So can you tell me, give me one point like that now? That's my question. So you know that 3 square plus 4 square equal to 5 square.
Yeah, so 3 by 5 and 4 by 5.
Okay.
And
But now
also the
now
negative one will also work now. Like it's a
no,
square.
no. 3 by 5 plus 4 by 5 is working, right?
3 by 5 square plus 4 by 5 square. Yes.
It is working, right? Okay. Now if I multiply it by t, is it work? That point.
No, it's the okay, wait. I mean, okay, 3t upon 4t you mean, but it will give the same
Ah,
thing.
yeah, 3t upon 4t. Yeah, like that. Both numerator and denominator I multiply by t.
It's the same thing, no? But
Same thing, right? Yeah. But
how is it?
my point, yeah, so it is same point, right? You are correct. You are correct. See,
Yes.
you can think of 3, 4, 3 comma 4 comma 5 as a point in R3.
Yes.
That is, you are looking a solution for x square plus y square equal to z square,
Yes.
right?
That
Right.
parabolic something.
Sure.
Okay.
Now, but for 3 square plus 4 square equal to 5 square, if I multiply by t, that means 3t whole square plus 4t whole square equal to 5t whole square. That is also true.
True.
Yeah. So, but you are you yourself told that all those points are corresponds to single point here.
Yeah, so we have to find different triplets now.
Yeah.
One
Okay.
solution
Okay.
will not work.
Okay. That's okay. That's okay. That what I want to say that there the line now equal to one point here.
Okay.
So that is what I want. I say before
The
starting of
line
this.
is a point. Okay.
So that is what I want to say that there is a thing called projective geometry. In future, you will come across a area called projective geometry. Their lines becomes points and planes becomes lines like that.
So,
Okay. Yeah.
I'm a bit familiar with this thing. So actually, you're taking a line, the whole line, when you were telling Viona.
Right.
So you're saying the whole line you're collapsing to a single pair of
Right.
antipodal points on the circle, right?
Right. And earlier you also told
Yes.
stereographic
Ah.
projection type. You remember?
Yeah, yeah, yeah.
So all these are connected. That's what I want
Hmm.
to just to say that. See, by end of this talk, you want to take certain things. This is one point. Maybe you may appreciate, right?
Hmm. Hmm.
Uh, Yeah, we will discuss more about them, but this is the right occasion, simple occasion to understand projective geometry. Big areas can be understood with a simple problem sometimes, right? Yeah, this is just one point. This you will understand later. You connect it in your future whenever you come across projective geometry. You come to this problem and try to relate. It will become easy. That's what Lalit is also telling what happens when z equal to 0. So that's what he knows actually. So there is a sort of equivalence relations, right, and all these things need to be brought, but I will not go into involve further. So yeah, Lalit, you can go ahead now. Yeah.
Yeah. No, sir, it's
Actually,
actually fine. Yeah. Yeah, Keshav.
I was thinking like we can characterize the Pythagorean triples, right, using a parameter. Then we will get different results.
Uh, I didn't get what you were saying.
So for example, like if we have a parameter like t square minus 1 over t square plus 1 and 2t upon t square plus 1, then they will always be a solution.
Yeah. But yeah, that's good. But okay. Yeah, there are many like ways to solve like this particular equation. But what I'm trying to do is I'm trying to illustrate how this would connect to the higher degree. So this
S-
method is useful in the fact. Yes.
yeah. Okay. Good. Good. No. Actually, sorry again. I'm unable to control myself. What is actually Lalit want to say is this thing. See, you can solve by different methods. For example, you know number of primes are infinite. There are different procedures. So Euclid give one proof. But why people now looking Euler's proof? You know Euler given that Euler summation formula. You remember that?
Yes, sir.
Now why that formula is more important? People why that is little complicated actually to prove that primes are infinite. But people like that. Means one side we have summation, other side we have a product. Euler summation product, Euler product formula, right? Why that one is important? Okay, that is important because this Euclid's formula is difficult to generalize to other numbers. For example, Dirichlet asked that question, right? So I take an arithmetic progression, and there I want to find infinite number of primes. So Euclid type method is very complicated to prove by that approach. Means assume there are only finite and multiply, add plus one to it. People tried that approach, and even there is a person called Ramurthy, Professor Ramurthy, gave a nice criterion that when we can do, when we cannot do by Euclid's approach. Okay, so I will come to that later. Yeah, so yeah, that is what I want to tell you. Right here in this particular case, it is better that we have this approach. This approach generalizes to many other problems. That's why this one. I'll come to you. I'm getting a phone.
Okay.
Lalit, may I ask
Uh,
you something?
yes.
See, when you said about that z equal to 0 thing, so when sir talked about projective thing, I thought that you're going from R3 to RP2. Uh, so
Uh, I would not actually be. I wasn't sure about everyone's background, so I'm not going to introduce a lot of projective geometry. Uh,
okay. So
yeah, that is.
just
Yeah,
yeah. Go on.
yeah. Yeah, I thought that we could just end with some computation. So I would
Okay.
not be proving everything.
Mm-hmm.
So that's why we don't require projective geometry, because uh, it would be really difficult to understand it in 1.5 hours.
Yeah. Okay. Yeah, I understand. Okay.
So yeah, Professor Ramamurthy actually has this really nice problem book in algebraic number theory. So if anyone wants to like take a look at it, it's a good book. Yeah. So anyway, so the simplification gives us this like equation, and as someone previously told, we know what the sum of the solutions is going to be. So using that, we know -1. So if alpha is the another solution of this equation, then -1 plus alpha is going to be -2m squared by 1 plus m squared. And if m is rational, and we suppose m to be rational, then alpha is also going to be rational, right? And this is the amazing thing. So you have, if you put a rational line to a rational point, then the second intersection point is also going to be rational. And we know that there would be two intersections unless the line is tangent to the curve, because of the nature of conic sections, right? So alpha is going to be another rational number, and you could substitute this in the equation of the line right here. And since m is rational, then y is also rational. So you get a rational point by basically using nothing but some rational point that you found and a rational line. So this is a like really good method for yeah, and alpha is just this. So, so was everyone able to understand this?
Yes.
Okay. Mm, okay. So we just on that. Okay. So now this is an interesting question. Our whole analysis depended on this particular fact that there was a rational solution to that equation, x squared plus y squared is equal to 1. So can we find a rational point for every given conic? So this is a question if anyone wants to answer. maybe you can find a counter example.
Which
Could you?
was what
Yes.
was the equation which we are solving for? That ax square one.
That was the equation of a conic. Okay. Yeah.
Okay, this equation.
Hmm. So don't take the general case. Just try to find some specific example. Uh, Something really simple. Just take some conic section maybe. Or this is a hint. The you can modify the equation of the circle in some way to find a counter example.
X square plus 1 is
Hmm.
equal to 0.
Okay, that's a good point, right? So for this we don't really have any. Uh, uh, okay, maybe something that involves y as well.
X square is equal to 2.
What?
X square minus 2.
Yeah, something that involves y as well. Some power of y.
You can ensure that this so x square plus y square is negative. But is that what you're looking for?
Uh, yes, that's a very trivial case though.
Yeah, so
So
what
for example,
could you remind us what a conic is, please?
what?
Could you remind us what a can you hear me?
Yes, yes.
Yeah, could you tell us what a conic is, please?
Uh, so equations of this form, like f of x comma y, this is the equation of a rational conic.
Okay, so this is what you're calling a rational conic. Okay, all
Yeah,
right.
A,
Yeah,
B, C,
Lalit,
D, E, F are that. Yes.
yeah, I think x square plus y square equal to 2.
Yeah, yeah. That's exactly what I was looking for. So it is, and this is not trivial, right? It's not trivial to see if it would have rational solutions or not. Actually, I took this example, but the essence is the same. So, okay, x square plus y square is equal to 2 has a rational solution. X is equal to 1, y is equal to 1. So, that would not work. We have a rational point for it. But this one will work. So, you can't find any rational solutions for this. And this is a really nice exercise. Uh, you can just do what Fiona did. So you can just convert. You can write small x as capital X by capital Z, and small y by capital Y by small y as capital Y by capital Z, and solve this for integers instead of looking for rationals. And yeah, this is a very good exercise. You should try it. So okay, any questions? Okay, so okay, so we had that case of a conic. Okay, so conic basically is an equation of the form summation a. So you basically have different coefficients, and associated with them um are powers of x, y. So x is power I, y is power j, where I plus j has to be less than or equal to 2, right? And I and j both can be 0, 1, or 2. So that is the general equation of a conic. So a cubic, what would a cubic like look like, if anyone can guess what the equation of a cubic would look like?
I mean the same thing, the sum of aij, sum aij x to the I, y to the j, and you're putting the restriction that ij are between 0, ij are not negative, and the sum has to be less than or equal to 3.
Yeah, that's correct. And so we can write it like this, right? So this would be the general
Yeah,
thing.
this one. Yeah.
Okay. And all these coefficients again, because you're obsessed with rational numbers, all these coefficients again are rational numbers. So we have 10 coefficients. But if you have not noticed till now, like this is a really complicated thing, right? We don't want to deal with such a big equation. Even when we were in six terms, we had 6 terms in the cubic, in the conic, and everyone was obsessed with removing the xy term, right? Getting rid of the xy term. So this is what we're also trying, what we will do for this cubic as well. But I would not go too much into the details because that would require some projective geometry. So you just have to take my word for it uh, at this point. So it turns out that you can transform this in a similar way that you remove the xy term. You can also transform this to remove a lot of terms, and you use a lot of projective and birational transformations. So the point that someone referred to earlier, I'm sorry, I don't know. I'm not able to recall names because I don't see the names there. So someone pointed this out, right? We can just shift the thing. We can just shift the circle, for example. But we don't know if under that
Yeah, it is Ishan.
yeah, Ishan. Okay, so Ishan said that under that transformation, maybe the rationality would be preserved. So birational transformation are exactly that. We are dealing with transformations that preserve the rational point. So if you had a rational in that cubic, after that, after some transformation, that uh, under that transformation, that would convert to another rational point. So the rationality would be like you would, yeah, you would have saved it. So the problem of finding the rational solution of this really humongous cubic reduces to solving the to finding the rational solutions of this really smaller equation, and this is called the Weierstrass form of uh, of the cubic, and it's this. So using some transformations, you can convert the whole thing to this thing. But again, don't be fooled by the size. It's again very difficult to find rational solutions of this as well. So this is called the Weierstrass form. And yeah, and this is actually the equation of an elliptic curve, provided that some certain conditions are obeyed. So if anyone has any questions. Okay. So I will be describing what the conditions are in a second, but you just kind of remember it like this: y square is just a cubic in x, where the leading coefficient is 1. Okay.
I have one question, Lalit.
Yes, sir.
Is it y cube is there in the original equation?
Yes, sir. Right here.
Okay. Means after transforming y square is coming. Is it true or not? I have to check, but okay, just I'm confirming with you.
Yes, sir. After transforming y cube.
Okay, means y cube also will go as a y square. That's okay. Anyhow, so you can go ahead. I'm not able to recall that
Yeah.
y cube will be there in the original equation also or not. That's just confirming with you. Okay,
Okay.
fine. Go ahead.
Yeah. So you have to have like you have to know some facts about the field we are working with to be sure if you can do this transformation. So actually, this can be even reduced further, provided that the field that you're working with has doesn't have the characteristic 2 or 3. Uh, so since we are working with rationals, we know that the characteristic of rationals is 0. So in that case, we can reduce it this even further. So it depends on the field that we're working with. I think there is after transforming, I think in the like if we don't know anything about the field that we're working with, maybe the y cube term remains, but even I'm not sure. Okay, so this is the Weierstrass form, and okay, so now we're doing the same game again. We're playing the same game. We're trying to obtain rational points in cubic curve, and again, if someone has an idea how to deal with this case, And remember the hint that I gave you, that somehow we have to use that same method that we use for conics for degree 3 as well. Uh, so if anyone wants to answer. Okay.
What will be the relation between roots here in cubics? Oh, sorry.
Okay, so sum of three roots. You know what that would be? What the three roots of a cubic?
Maybe A here.
It Yeah. So if you have cubics that looks like ax cubed plus bx squared plus cx plus d is equal to 0, then the sum of the three roots would be minus b upon a.
Hmm.
Okay. So suppose you find a rational point on the cubic. Suppose that you find a rational point on the cubic. What can you say then? What can you do with it? Can you draw some line through it? Maybe a rational line. What would happen then? Just a guess.
Maybe it will intersect twice.
Uh, Apart from the point that we started with,
Yeah,
yeah. So it will basically, that line would be intersecting the curve thrice. And why would that be?
we are solving cubic, right?
Okay. So if you have, you basically, what is a line? Line looks something like y is equal to mx plus c, right? As we tried before. And if you substitute the y in this equation, you basically get a cubic, right? Can even everyone see that? Like that you would get a cubic in x, right? So you get a
Yes.
cubic in x. Yeah. So you get a cubic in x. So now what you can do is just see what the sum of the roots would be. So suppose you had one rational point. Can you say that the other two points would also be rational? The other two intersection points of the line with the cubic.
Either they both be rational, I think, or none.
Okay. Yeah, that is correct. So, but we can't say with it with certainty, right? As you said, either both of them are rational or both of them are not.
Yeah,
Yeah, because in cubics, rational roots and even imaginary roots occur in pairs, right? So if you have one rational root and sorry, irrational roots occur in pairs. It's something like that. I don't remember the exact thing. So anyway, if you substitute y as mx plus c in this, you will get a cubic, and you know the sum of the roots would be some rational number. However, if you just take one point, if you start with just one point and you put a line through it, then it doesn't guarantee that both the other points would also be rational. So how can we remedy this? How can we make sure that the point that we get is rational? So what you need to do for that is actually take two rational points. So if you find two rational points on the curve and you put a line through it, then can you say that the third intersection point would also be rational?
Yes, maybe because if that one will be irrational, it has to come in pairs.
Yeah. Or simply the sum of the roots is rational, right? So you just take the other roots on the right hand side and you have the third root as a rational number. Is that okay? So if
I didn't understand last point.
okay, so if alpha, beta, and gamma are the solutions, then alpha plus beta plus gamma is going to be some rational number, right? As I said, minus b upon a in that cubic, ax cube plus bx square plus cx plus d. So if alpha and beta are rational, can we say that gamma would be rational? Because it's summing up to a rational number as well.
Yes.
Yeah, that is clear, right? So gamma would also be rational. And since the line we were using was also a rational line, and we substitute rational x in it, we will also get a rational y, right? Y is equal to mx plus c. Is that also clear?
Yes.
Yeah. So you have a rational point, right? X and y are both rational. So if you take two points, two rational points, you get a third point is also rational. So that is the trick to this one, to degree 3. So you have, instead of starting with one rational point and a rational line, you need to put a rational line through 2 points, and obviously this line has to be unique. So yeah. So this is just what we just talked about right now. And if P and Q are rational points, we will denote the third intersection point as P star Q. You can interpret it as like some operation, right? So P star Q is just the third intersection point. Okay. So yeah. Okay, this is maybe this is obvious. So basically, since elliptic curve preserve the rational points, we know that the P and Q that were on the cubic, they under the after the transformation, they would get transformed to P dash Q dash, which would also be rational, and P star Q was rational. Therefore, P star, uh, sorry, uh, P star Q was rational. So P dash star Q dash would also be rational. So under the transformation, we can use the same procedure. That's clear. Okay. So just to give you a feel for it, so this was the equation, right? So this is what like typical elliptic curve looks like. Okay, so this part is called an egg, I think, and this is called the infinite component. It's not necessary that every elliptic curve has an egg. So this is another example in which you don't see a like circle like thing, so it's not there. So from the equation, could you think about like the structure of what what the uh, elliptic curve would look like in the real plane, like from the equation? Could you like make some uh, observations about it? So this was the equation. Can you like make some observations about what like for example, if x comma y is a rational solution, can you like is a point on the elliptic curve, can you what can you say about x comma minus y?
This is symmetric kind of about x-axis.
Yeah, that is correct. So yeah, this is symmetric, or it's exactly the reflection, right? Because x comma y is a point, then x comma minus y would also be a point, because the negative would just because it's y squared term, right? So it's the yeah. One more thing that you probably would have noticed is the intersection that it has with the that the elliptic curve has with the x-axis. So here there are 3 intersection points, and here there is only one intersection point. Can it have 2 intersection points? Okay, maybe that is a wrong question to ask right now. Okay, so okay,
We
ignore.
will put equal to 0, and we are looking at solutions of x cube type. So from that, um, no,
Yeah,
sorry,
from
let me
that
think.
Okay. So okay, so I'll leave that. But these are just two examples of an elliptic curve. And okay, Viona, I'll move on because if you have an observation, you can like share it with us.
Yeah, please move on.
Okay. It turns out that this is not an elliptic curve, and uh, I'll tell you why that it is not an elliptic curve, and this is again not not an elliptic curve. So it is possible for like the in the Weierstrass form, you can find equations which have two intersection points, but
So because
they
it's
would
not
not be.
smooth, right?
Yeah, that's why it's not an elliptic curve, because we were considering elliptic curves were smooth. So these are also called singular points. Okay, so this is called a cusp, and this is called a self intersection, and these points are called singular points. And by definition, singular points are the points where the partial derivatives with respect to x and y both vanish for a particular curve. I'll okay, which are not allowed. We're only interested in curves which are non-singular. So non-singular basically means it has no singular point. A curve which has no singular point. So this is the test for singularities. And if you just rewrite the equation of the elliptic curve, so suppose small f of x is just cubic, is just the cubic that we talked about, the x cube plus ax squared plus bx plus t. That is just small f of x. And capital F of x comma y is just y squared minus small f of x is equal to 0. So the if a point is singular, then partial derivative of this capital F with respect to x and y vanish simultaneously, and they are also present on the point on the curve. That point is also a solution of this capital F. So for example, if you have this curve, can someone guess what the equation of this curve would be, like from the geometry? Because -1, it's intersecting at -1, x-axis at -1 and 0. Can someone guess what the equation of this would be in Weierstrass form?
Yes, y square is equal to x into x plus 1.
Okay, not really. Remember, this is like a double intersection point. So uh, you can take another
So
guess, or
x
maybe
square
you
in
can,
place of x.
yeah. So y squared is equal to x squared into x plus 1 is the equation of this elliptic curve. Again, for this is really simple.
Y square equal to x, right?
Uh, y squared is equal to x cubed, because we have triple like
Ah, yes, of
intersection
course. Yeah. Sorry. Yeah.
okay. Y squared is equal to x is just parabola. So okay, so you have these two different kinds of curves, and you can check the partial derivatives. So if you have, for example, y squared is equal to x cubed, then y squared minus x cubed is equal to 0 is the capital F. And if you take the partial derivatives with respect to x and y, they both vanish at a particular point. And can someone tell me what that point is? You can also guess from the graph.
Well, they're vanishing at 0, right?
Yeah, they're vanishing at origin, because the partial derivative with respect to y would be 2y, and with respect to x it would be minus 3x squared. So if x is equal to 0 and y is equal to 0, both are vanishing, and they're also present on the curve, because 0 comma 0 is a solution of y squared is equal to x cubed. So we have a singular point, and that's why this fellow is not sadly an elliptic curve. And for this, we had the equation y squared is equal to x squared times x plus 1. So again, you can apply the same procedure. So if anyone wants to tell me the singular point.
The origin again.
Yeah, you can guess this from the graph, but I just wanted you to calculate the partial derivative. So okay, so that is the test for singularities. Singularities basically mean cusp and self-intersection, and they're not allowed in elliptic curve. So we kind of have this a partial definition. The actual definition is a little it's not easy to get, and I would need more time to explain one of the terms in that definition, which is genus. So uh, so we're not going to be I think Ishan to ask the definition in the beginning. So we're not giving the actual definition, but an elliptic curve is just, at this point you can just think of it as an equation of this in this Weierstrass form that is smooth. Okay, so that is like kind of partial definition an elliptic. Okay, so now obviously you are thinking, why are we not letting this uh, poor thing be an elliptic curve? And there are two reasons for it. So uh, okay, so for example, y squared is equal to x cubed. Can anyone come up with like a really simple method to find rational points on this? Like y squared is equal to x cubed. So what is some really simple method to find points on this? Rational points on this.
Put squares for x so that y
That is
is
very
also.
clear. Yeah, that is very quick. Okay. So you just parameterize it. Okay. So x is equal to t squared and y is equal to t cubed. And if you have any rational t, then t squared and t cube are also rational. So you would get infinitely many solutions. And similarly, you can also find some parameters for this as well. So that means that these cases are easy, but again, uh, there is one more problem, that we are trying to find a kind of uh, we're trying to convert this set of rational points on the elliptic curve into some kind of group, and it turns out that uh, this thing is no longer a group. The set of rational points is no longer a group if you have singularity. So that's why we're being very particular about the singular points. So I'll be defining what the group operation is in a minute. So there's just two reasons for it. Yeah, I would also like to just point out that many things would make sense after you've like completely listened to the talk. So don't get upset if you don't get something like right now. And there would be a lot of things that even after the talk they would not be clear, because this is an active area, right? So there are a lot of open questions. Like if you just like scratch the surface, you may find an open problem. So just be very patient about it. Okay, so now we're trying to define a group structure on rational points on elliptic curve. So, and we are like calling the group operation as addition as usual, and P and Q are two rational points on an elliptic curve. Then P
Lalit, can
plus
I
Q
say
is,
one point here?
yes, sir.
Yeah. No, what I want to say that, as you are telling actually, that so one can think of this another approach also, because sometimes exact definitions is not possible to give and all if you feeling. So to overcome that, I'm just asking, look at in another perspective. You take a single equation, single variable, right? So now I solve it and I'll find all its roots. So if you go to complex numbers, I'll get all the roots, right? By fundamental theorem of algebra. So now I want to find equations in one variable such that all its roots forms a group. Is the question clear to all of you? So can you give me one equation in one variable and whose all its roots forms a group.
X
So
equal
you
to
are
Yes.
0.
The
x equal to 0 is 1. Okay, good. Yeah, go ahead.
okay. Then x square equal to -1, so the roots of unity.
Roots of unity, x power n equal to 1, right?
Sorry, yeah.
X power n equal to 1 is exactly the set of all nth roots of unity. So there it is a cyclic groups, right? So you know that cyclic groups are coming from the roots of an equation actually, right? For every n there is one cyclic group that comes from the nth roots of unity in the part of as a part of multiplication, right? So sometime I asked this question to myself. Okay, then are there any other equations in one variable? So I found that still one can see that we cannot find any other equation, right? Okay, you can confine to one group operation, right? Yeah. So similarly, now if I go to that x square plus y square equal to 1, polynomial in two variables in two equations, each set of all the roots of x square plus y square equal to 1 forms a group. So you can see that that is e power I theta again. Are you
Yes,
following?
okay. Yeah.
Yeah. So if I take 2 points on it, e power I theta 1 and e power I theta 2, is that
Huh.
again a group? Again, if I multiply, again it is a
Again,
root.
multiplication you're taking, right?
Yeah, again multiplication. So again, there are also nth
Yes,
roots
it
of
is.
unity.
It
Right?
is. It is.
Yeah, right. So that is called circle group, right? So people
Hmm.
denote it as S1, right?
Okay. Yeah. Okay. So you're taking S1 in terms of complex. Okay. Yeah. Okay. Yeah. Yeah.
I'm just connecting. So
Ha ha
maybe
ha.
different ways to look at, right?
Yeah. Yeah.
Now
Yeah.
similarly, I'm asking this question that when this type of equations will form a group, right? So exactly that when it is non-singular and put some condition, then only it becoming a group. That is, I think maybe Lalit want to explain you much more better way. That is what he is actually telling, that he want to bring the group structure into that. Then it demands that it should not be singular, right? Yeah. Is it okay, Lalit? Please go ahead. Yeah.
Uh, yeah. So, okay. So, can anyone tell me why? I think. So, can anyone tell me like why group theory is in continuation of what Satya sir said? Maybe. So, why is group theory uh like why are we so obsessed about classifying things as groups? Maybe like what good does that do? Like generalizing everything.
I don't know about what
Because
your. Yeah, Viona, go ahead. I'll speak later.
no, you say first.
Okay.
Yeah.
Actually, I don't know. I'm not very sure about your question. If you're asking me some places where seeing things as groups helps, then I can give an example. But I'm not very sure about why groups help as classification.
No. Like classifying things as groups. Like if you like have some structure, like if you
Mhm.
have some set with a particular operation, and
Why does it
then
help to make it a group?
yeah.
I can give one example of a very famous thing. So that Brouwer fixed point theorem.
Okay.
It's a question in topology. You have a disk, okay, a disk in R2. Any continuous function will have a fixed point. That's the theorem. That's what the theorem says. And you can solving it in topology is apparently difficult. So there's something called a fundamental group. Uh, so you can convert the topological. So essentially, this if you can take maps and you can say if there was no fixed point, then you would have a factor. You would have the identity homomorphism from Z to Z, but it would factor through a trivial group, which is not possible. So this contradiction will establish that the theorem is true. So this is one place where it helps to convert a set into a group. That's essentially what I'm trying to say.
Yeah. Well, I don't know topology, so I didn't understand anything. But
Okay, sorry.
yeah, no problem. But the essence of it is basically that mathematicians have been working very hard to like uh, work on general groups, and the reason is that if you, for example, if groups weren't there and you had to like figure out the properties of some group, then you would have to like figure out every property from scratch again and again and again, depending on how many sets you are working with. But the good thing about groups is that you already know a lot of properties, right? The mathematicians have been working on it for a long time. So if you just, the answer is much simpler, right? If you just classify something as a group, then you can put in all that effort, like, and all that knowledge of groups to this one small like example. So that's how it helps, right? Basically, the generalization helps us with specific examples. So there's this kind of weird relationship between abstraction, like general things, and specific things. So specific things can be understood by generalization, and general things can be understood using examples. So if you're working with groups, you would not have understood everything if you're just like had the properties told to you, like just the group axiom. That would not have uh, done anything to better your understanding. But as soon as you found that there is some example, so for example, the integer set of integers under addition, as soon as you found that example, a lot of things were clear, right? And suddenly you could talk about the generators of Z. You could talk about the subgroups, and there were so many things, right? So many group theoretical things that you could think about for Z. And Z, maybe Z was used to construct, maybe it was an example to construct groups, like that particular definition. Because definitions, uh, as you probably know, it takes a lot of time to decide what definition to use. So, for example, uh, uh, the I forgot his name again. Uh, the person who mentioned topology.
Oh, Ishan.
I'm Ishan.
Yeah, Ishan. Sorry. So as you said, you mentioned topology, right? But if you when you studied it, you must have thought about how they came up with the definition of a topological space. So
Yeah,
it
yeah,
takes
yeah.
a lot of, yeah, it takes a lot of time to decide what definition to use. So nothing too general, in which case the definition would be small, and not something very specific, in which case the definition would be really big and you could work with only a specific thing. So yeah, but that's why we are trying to form like a group structure on the rational point. So we can use our knowledge of groups to on elliptic curve, on rational points. If P and Q are rational points on elliptic curves, then P plus Q is just P star Q star O, and star is just the operation that I talked about earlier. So if you have points P and Q, then P star Q is just the third point of the intersection. And O is the point at infinity. Yes.
No, so this O, when you're saying point at infinity, are you again talking in terms of projective plane, that point, stereographic projections, that point?
Yeah.
Okay.
But again, I would not be like going into like
Yeah, yeah,
what
I
it is and
understand.
how to manage. Yeah. I'll just like tell you how to find P plus Q. Okay. I'll not be going into like yeah. So P plus Q basically means that it is the reflection of P star Q along the x-axis. Okay, so just remember this in terms um, of variables. So P star Q is x comma y, then P plus Q is just x comma minus y, and we know that point would always be there because of the nature of elliptic curve. Because it's, as Fiona said, it is uh, it's a mirror image along the x-axis. So basically, O is the point at infinity, and if you like put a parallel line, uh, uh, a line parallel to y-axis, then it intersects the elliptic curve at 2 points, right? But this third point that it intersects at, which we call the point at infinity, is is actually considered also to be on a part of the elliptic curve. Just like take my word for it or something. Like just remember it for now, so that we can do interesting things later on. Uh, I'll put some like references about this in maybe I'll when I will post the slides. So I'll put some references about projective geometry. But for now, just take my word for it, okay? So P
Is
plus Q
O
is,
also
yeah,
this point O, is it also a root
of, yeah,
or
yeah, it is. It is a part of the elliptic curve. Because we want the every line to intersect this elliptic curve at 3 points, right? So if you have already 2 points, then you need a third point, and that third point is a point at infinity. Okay. All
I
right.
didn't understand completely, but let it be.
Yeah. For now. For now. So okay. So we have the point at infinity will be considered to be part of all elliptic curves. Okay. And yeah, I just talked about this. Every line would meet at O, and you obviously know in projective geometry, no two lines are actually parallel. They meet at the point at infinity. So if you draw lines parallel to one another, which are in turn parallel to y-axis, they would meet at the point at infinity. And yeah, this is important. So O star O is equal to O. So basically, if you take a line which is going through the point at infinity twice, then the third intersection point is also O. Again, this is called the line at infinity, and don't think too much about it. Just like kind of remember it for now. Okay. So okay, so now we are going to prove that E of Q is an abelian group. So I hope everyone understood the operation. So like we'll try to prove that the rational points form an abelian group, the set of rational points on an elliptic curve. So can anyone tell me how we'll prove closure? So if you have two rational points, P and Q, is P plus Q, which is P star Q star O, also going to be a rational point on the curve?
It will, right? Because P and Q will satisfy this equation, and P plus. So this curve that you had, you can split it up into. Just one second. Can you go to the curve, please?
To the curve like there.
I mean, when you were talking about that Weierstrass form.
Oh, okay. Mm, yeah.
Yeah, okay. I think no, what I was thinking is wrong. So what I was thinking, if it helps, is that individually each rational point would satisfy the equation. So if you
Mm.
add the two equations, you'd still get that the net is zero. And then I was thinking that you could combine. Uh, so if I take an example, it will be a bit better. So let's say the curve is gamma. Okay, so gamma of x is zero and gamma of y is zero, right? Because those are two roots. So gamma of x plus gamma of y is also zero, and I want to say that gamma of x plus gamma of y is actually gamma of x plus y.
Uh, okay. So actually, addition is not like the usual addition.
Yeah, that's
Uh,
why I thought later on that it's wrong what I'm saying.
yeah. So the
Can you
addition
tell
is
me
just
again
yes.
what does P star Q mean here? Multiplication?
Piece multiplication. You can call it multiplication, but it's basically you putting a rational a line through rational points P and Q, and the third
Hmm.
intersection point is P star Q.
With
I
the
think
with what?
okay. This
What?
we talked about this, right?
Okay, it's that.
Yeah, I should have mentioned it like later on as well. It kind of all got mixed. So the P star gives the third intersection point, and we know that the third intersection point is rational, right? We showed that. So everyone remembers that, right? That if P and Q are rational, then P star Q is also going to be rational. Using the sum of roots, we proved that. Does everyone remember that?
Yeah, but just 1 second. We had done it only for square, quadratic and cubic. Uh, I'm actually a bit confused. Are all elliptic curves either quadratic or cubic with some additional conditions?
We okay. So an elliptic curve is just transformed cubic.
Oh, it's
We
just a
just
transformed
transform
cubic.
the,
Okay,
yeah.
okay. Yeah,
Basically,
then what is, yeah.
basically when you're thinking about cubics, just think about elliptic curve. As long
Okay.
as you are trying to figure out the rational point, it's fine.
Mm,
They're
okay.
similar.
Okay. Then yeah, you had said that the sum of the three roots will be minus b upon a, which is a rational, and two
Yeah,
of them are in anyway rational, so the third one has to also be a rational.
yeah. So okay, so what we're trying to do is we're trying to see if the set of rationals is closed. So how do we prove that? So suppose we have um, P and Q uh, are rational, and P star Q is just going to be, let's say, some point x comma y. Okay, we're supposing that P and Q are rational, so P star Q is also rational, and P star Q star O, which is P plus Q, was x comma minus. So if x and y are rational, then x comma y is rational. That means x comma minus y is rational. So that means closure holds, right?
So Lalit, do you have any picture with you related to this? Means first to draw
Uh,
the line,
yeah.
they will meet and draw the parallel line like that. If you show that, it will be little bit convenient if you have already.
Sir, I have like the book. Maybe I don't have a picture on the laptop, so
Okay, okay, okay.
I should have put like a picture. That would have been easy.
That is very useful actually. So
Yeah,
you take 2 points on the elliptic curve and you draw the line and it touches at one point. Then again you draw the line which is meeting the O, right? That point and meeting O. And it meets the curve at another point. That is the point actually you are looking for. To explain that, it is better to have a diagram.
yeah.
Yeah,
Uh,
okay. Yeah.
can
So,
you see like this? Is this visible?
no, not visible actually.
Oh, okay. So I actually don't know even how to write on this. Otherwise, I would have like.
That's okay. That's okay. You can carry on. So later they can search somewhere. Yeah. Yeah. So I think you people can open Wikipedia site elliptic curves. Maybe. Yeah. So you continue.
Okay. I was,
Sir,
Uh,
maybe what could, if Lalit could download the book from LibGen and then just share the screen?
yeah, that was what I was thinking. Should I do that?
no. You just carry on. So let us see. I'll suggest you that in the meantime, right? You just carry on. Continue that.
Uh, so we proved that if P and Q are rational points, then P plus Q is also rational, which basically means that the set of rational points is closed under addition. Addition is just again P plus Q is P star Q star O. Now the existence of identity, and it turns out that uh, that okay, so you basically need some point Q such that P star Q star O is P, right? Then Q would be the identity. So it turns out that the point at infinity can be taken as the identity because P star O is just going to be the reflection of P along the x-axis. So if x comma y is the coordinate of P, then P star O would be x comma minus y, and then you take then you again do the operation with the point at infinity. So P star O is equal to P plus Q, uh, P plus O, and that would give you back the point P.
Yeah,
So
so you can open a Wikipedia website, maybe that may help you to explain, maybe, right? ellipticus Wikipedia sufficient. Yeah, right. So go little below. Yeah.
Oh, this is good. Okay. Thank you, sir. So, so if you now you should be able to visualize it. If you have P and Q as rational points, then P star Q, which is R, is also rational, as we did earlier. And P plus Q is just the reflection of R. So if you just draw like line parallel to y-axis, you would get P plus Q. So now it should be clear, I think. And well, they haven't described like P plus Q actually. Okay.
So we did star O, etc. just to have an identity to make it a group.
The star is actually like a precursor to the addition, right?
I mean that O wala part which we took.
Yeah, O is just the identity. I'm not able to understand the question.
We could have only defined the operation up to P star Q, but instead we did P star Q star O also.
Yeah.
We also
P
reflected
star
it.
Q. Yeah, P star Q would actually not work. I don't remember why, but you can think about it maybe. The P star Q doesn't work. The composition just doesn't work. You need the additional zero thing as well, the point at infinity, to define the group. So, so should we take like a break?
Yeah, means actually now not many slides are there, right?
Yeah, but okay. So, all right. I'll just come like in 2 minutes.
Yeah, yeah. Okay, good. So here, since he is not available, so I want to say a few points here. He's telling about cryptography, so let us try that part. Okay, so in the cryptography, there is a problem called discrete logarithm problem. Okay, what is discrete logarithm problem? If you take a cyclic group, so cyclic group is generated by some element G, right? So now if it generated by G, and I take some element H in that group, capital G, and it is generated by small g. So now G is equal to, sorry, H is equal to G power X for some X. So now how do you express in the logarithmic terms? Can somebody help me? G power X equal to H.
So log H is equal to X log G.
Sorry, can you repeat? So I am telling again, I'll repeat. G power X equal to H. G is the generator, right? G power X equal to H. So you remember the 10 square equal to 2. So log 100 base 10 equal to 2 you write, right? Am I correct?
Yes.
10 square equal to 100. So log 100 base 10 is equal to 2. So like that, can you convert and tell me? G power X equal to H.
So X is equal to log of H to the base G.
Right. So that is called discrete logarithm. Okay. Logarithm converted into like this. So now the problem in the group theory is that so I gave you G, I gave you H also. So find X. That is not that easy. If your group is very large, and then it is very difficult. Okay. So that still no polynomial time algorithm is available. That is called discrete logarithmic problem. Is the problem clear?
X is an integer, no? Means
See, you can think of like this. For example, you take a large prime P, right? Then ZP is a cyclic group, right?
yes,
And
means G raised to
it has a
X.
generator.
How
Yeah, it is. Yeah, please go ahead.
how is G raised to X defined? Means multiplying G X times. So X is an integer, no?
Yeah, okay. Yes, integer. Okay, you can think of that way in the ZP, right? Yeah. Now that part is
Yes.
okay. Yeah. So now that number I need to find out, X I need to find out, but that is a very difficult problem. In general, if I give G as well as H, then finding X is a difficult problem. Of course, I need to prove why it is difficult, but I want to say that till now there is no polynomial time algorithm to find that. That is what Diffie and Hellman, two people figured out that. And they proposed a key exchange that is called Diffie-Hellman key exchange problem, right? They figured out that. And with that we can exchange the keys. In the cryptography, what happens is that Alice and Bob, two people will be there. They want to communicate secretly because they will not believe internet and all. So there is some sort of somebody will leak get the information. So to convert it into so original message converted into ciphertext, and then it is sent through via that channel. So but to convert, then I have to decrypt. That is called encrypt, then decrypt. So to decrypt, then first they need to have a key. So with that key, so in order to exchange keys, up to that extent, 1976, Diffie-Hellman wrote a paper. So till now there is no, so everything is by symmetric, means they meet physically before and share the secret, then they communicate. Now new techniques came, right? So now before ellipticals not introduced, so people are working in those groups only. Then the key, I had to take very large group, because in the small groups I can by brute force I can get it the key, right? So they have to go for a large group, and all that theory is there. But whereas if you come to elliptic curves also now he is going to prove it is a group, and it is a abelian group. Now here it is group with respect to addition. So instead of power n, now we have into n will come. So that is also people are using discrete logarithmic problem for the elliptic curves. Okay, so that way elliptic curves are used very much used in the cryptography. Not only that one, there is other things also. I want to factorize given number. I give a number to you, then so that is also open. Given a natural number n, we know that it is written as product of distinct primes, but people not proved that how there is no polynomial time algorithm again. That is used in RSA cryptography. There is a cryptography cipher. So RSA cryptography that will be used. Okay. So, but whereas the elliptic curves are here, key size will be small and very effective, because the group structure is complicated, right? First I am adding, and so that complicated structure helping us to reduce the key size. That is the advantage. So the whatever the difficulty you are facing in understanding the group, that is useful for the cryptography. That is just I want to convey before Lalit came, right? Yeah. Lalit, are you there?
Yes, sir.
Yeah. Now you can carry on.
Uh, uh, so okay, screen. So right, so all right. So what we're trying to do, okay. So we've figured out that the identity was just the point at infinity, and so because P star O is coming out to be P, and again now we're talking about the inverse. So can anyone guess like what the inverse might be? Uh, so we basically want a point uh, Q such that P star Q star O is equal to O. So any guess? Okay, so if we consider like the reflection of P along the x-axis, would that work? So what is P star the reflection of P? So if you have P and you have the reflection of P, and if you like find the third intersection point, what would that be?
It won't intersect, maybe.
Yeah, we talked about like how the reflection and that point would intersect at point at infinity.
Okay, that is defined as O.
Yeah,
Okay, then it's O.
yeah, it's O, right? So we'll just refer to the reflection as minus P. So P star minus P is O. And what is O star O? Again, I think I recalled it here. O star O is just O, right? So that means that if you have P and minus P as x1 comma minus y1, then P star minus P star O is just O star O, which is O. So that means the reflection of P along the x-axis is the inverse of P. So hope that is clear. So we basically have the identity, we have the inverse, we have proved the closure, which means this is the binary operation. So, and we're trying to prove that E of Q is in abelian group. So this part is easy. So can anyone uh, is this going to be commutative or not? So can you prove commutativity?
Yes, probably. Um, it's a line that is going to intersect. So any way you draw it, starting from PQ or QP, it will intersect at the same thing, and then you do star O. That is, you reflect. You should get the same point.
Yeah. So that means basically what we are trying to say is that P star Q star O is equal to Q star P star O. So that means P plus Q is equal to Q plus P. So that means E of Q is in a abelian group. And okay, again, we have reached another point where you have to take my word for it. So the associativity is going to be true. And so the associativity is going to be true, and you have to take my word for it because it takes a long time to actually prove it. You have to take like cases. It's not straightforward. So we are going to skip this. So basically, we have like just like again, take my word for it that E of Q is an abelian group. Okay. So what I'm basically trying to lead you to is some computational problems because those are interesting. So we proved that E of Q is an abelian group, and now we can talk about E of Q in terms of group theory, right? So can anyone define what it means for a group to be finitely generated? If anyone has an idea.
If we take any element and raise it to some n, we should get back to the identity. Like everything is a finite order, maybe, and it is cyclic.
No, I would actually say the generating set is finite.
Okay. So finitely generated actually means that if you have a finite number of points, then all the other points in the group can be generated from it.
Okay, like a
So
basis span, something like that.
yeah, yes,
Yes,
yes.
yes. Actually, that's what Ishan is telling also.
Oh,
It is generated by finite number of elements. For example, you take integers, right? Piana.
Oh, yes, sir.
So now can you tell me what is order of 2?
Infinite.
No. So then, but it is finitely generated.
Ah,
It is
right.
cyclic.
One, right.
It's it is
Understood.
one is a generator. So every number is now expressed in terms of 1. So 10 is equal to 10 into 1 only. 1 is like, as you correctly point out, 1 is like acting like a basis for the Z, right? So 1 plus 1 plus 1 adding that many times. So here that power, raising power is same as adding. Hmm? But of course, so Z is actually, it is a free group generated by single element. Yeah, so I'm not going into free group and all, but that is an example since we discussed that. Yeah, please go ahead. Yeah.
Yeah. So yeah, Z is actually a good example. So so basically, if EQ is finitely generated, basically means that you can have some points such that you can generate every rational point. And it turns out that every rational point P can be represented in this way. So if P1 till PR are, okay, this is a mistake. It should be PR. Okay, not PN. So P1, P2 till PR, if these are all points of infinite order, and let's suppose T is a point of finite order, then you can represent every rational point in this way. So you can just keep adding P1 n times, and then add P2 n1 times, P1 and n1 times, and you can add to that to n1 P1, you can add P2 n times, and you go on till nr PR, and then you add T, and T is a point of finite order. So every absolutely every point on E of Q can be written in this way. And this is a theorem that Mordell proved in 1922. So, okay, so why do we have like this distinction? Why do we have points of infinite order as well as points of finite order? So it turns out that an elliptic curve can have points of finite order as well. So, like Fiona said, what if we just what if we just add something n time? So if you add like some point, uh, some particular number of times, it is possible that you can get the point at infinity, which is just true. So that's why we have this T element, so that we have some way to also include the points of finite order. But it's also possible that some points might have infinite order, right? So it is possible that you can just keep going and going, and you will never ever reach the point at infinity. And those points can be represented in this way. Some points need like the whole thing, but some points maybe like, for example, two times p1. So uh, if p1 has finite or infinite order, so 2 times p1 is something that can be generated using only p1. And T is the element of the torsion subgroup of E of Q. So torsion subgroup of an abelian group is just the set is just the group of points of finite order. So if you have an abelian group and you take all the set of all points of finite order in it, then it turns out that that set forms a subgroup. So that is what torsion subgroup is, and the set needs to the group needs to be abelian for that, for torsion subgroup to exist. And T is the point of finite order, is an element of torsion subgroup, and n1, n2 till nr are obviously elements of integers, and R is known as the rank of the elliptic curve. So it turns out, as you can probably guess, that you need only two things to actually write every rational point, and that is the rank of the elliptic curve and torsion of the elliptic curve. And if it turns out that the torsion is really simple to figure out now, it was not before, and there were a lot of difficult theorems that had to be proved um, for torsion to be completely understood. But the rank is still like really elusive, and many basic questions about the rank remain unanswered. We don't even know how big the rank can be. Uh, so, has anyone heard of Manjul Bhargav. Manjul Bhargava.
Yeah,
So, so you remember that in 2014 he got the Fields Medal, right? So
yeah,
he got the Fields Medal. He collaborated with one of his, I think, doctoral students, Arul Shankar. And Arul Shankar is from CMI. He did his bachelor's from CMI. So they both uh, prove that the average rank of elliptic curves is 1/2, I think. Or there's maybe some another thing attached to it. So we just know like very less about the rank, and it has led to a lot of open questions. And even the Burstinator Dyer PSD is also, which is a Millennium Prize problem, is also related to the rank of an elliptic curve. So Millennium Prize problem you basically solve the it's the most difficult way in which you can get like earn $1 million. So this is what I said earlier. This is a definition of torsion. The torsion subgroup of an abelian group is just the subgroup of G, which consists of all the elements of finite order. And you can prove that that it's going to be a subgroup using the subgroup test. So can anyone like would anyone like to prove it? Just using the subgroup test.
Okay, I'll try.
Yeah.
So the identity is there. It has order 1. Then if you take any two elements A and B, and if suppose they are having order, say A is having order M and B is having order N, then I claim that AB raised to M plus N should be the identity, because this is what do you call it, abelian group. And so AB must have finite order. So AB is there. And if A is having order N, then A inverse should also have order N. So they are both finite.
Yeah.
Yeah, so
So
one small correction here.
yeah.
It is a group with respect to addition, so not power n.
Yeah. Yeah. So okay. It's fine. Like
It's
just
fine.
for
Yeah, it's
proving
fine.
it.
Yeah, fine. Yeah, go ahead.
And
Yeah.
instead of
I
M
didn't
plus N,
understand.
no, sir
No,
is
Uh,
just
just
saying
I
that.
want you tell better you just careful that this is a group with respect to addition. So whatever the proof you given, it is correct, and it
okay,
is you
I
are
should
giving
use
for
the
general
operation
setup.
as A plus B.
Ah,
Like that.
yeah. Yeah. So it is better to have that also in consciously, even though you proved like this. But here everything is in terms of addition. That I want to point out.
Okay.
And one more thing, I don't think M plus N would work. Uh, do you see why it won't work? Because you would have
Or
uh,
MN,
A star.
MN. I should think.
Yeah, yeah, Mn would work. Okay, so okay, so torsion is clear. Uh, okay, so here you have a lot of details here, and I'll just okay, I'll not explain it anymore because the time is very less. So I'll just okay, so I'll explain this a little bit, and you can work on this later after the talk. So if you have P1 and P2 as two rational points, then try to figure out what P1 plus P2 is going to be in terms of coordinates, right? That is exactly what this addition formula is. So try to find this formula. And if you've understood like how we're getting P1 plus P2, it is not very difficult to get this. So just try to find this addition formula. And also try to figure out what would happen if we just duplicate a point. So instead of taking two different rational points, what would happen if you just take p plus p? P is some rational point. So and also try to derive this equation, like just duplication thing. And uh, okay, I'll skip this. So if you go through this afterwards, you should be able to get it. But just try to derive these equations. because then you can do a lot of fun computation. And I should probably explain this a little bit.
So
So
I
as I
have one
said,
question. I have
yes,
one
sir.
question. Can you go to before slide? Slide before. It is not related to subject. So how do you get this red color here for this particular this one in the LaTeX?
Oh, I was, sir. I'll mail you. I don't remember.
Oh,
There are
that.
like 3 different options. So you can get blue,
Actually,
red,
see, one is that. Okay, okay, yeah, okay, fine, yeah, fine. Go
and
ahead.
it's the theme is, I think, Berkeley something. So
Okay,
you can
okay.
use that theme and get.
Okay, okay, okay.
Now we have like some theorems for computation. So as I said earlier, that the Weierstrass equation can be further reduced into this equation. Uh, if the field that we're working with doesn't have the characteristic 2 or 3. So since we're working with rational numbers, which has the characteristic 0, we can reduce that equation further into this equation: y squared minus x cubed minus ax minus b. So basically, the x squared term has vanished, and where a and b are also integers. And we have this thing called the discriminant, and this is also another exercise, uh, that if just try to just take this curve and try to see what is the equivalent condition in terms of coefficients that you would have for there being no singular point. So if there are no singular points, what would that mean? And it turns out that if a curve has no singular points, then that means that the discriminant, which we basically, this is a different discriminant from the quadratic equation. So just 4aq plus 27b squared is non-zero. If yeah, if there are no singular points. So this is just another thing. I'll be going really quick because these are all things that we're not going to prove. So if you want to do computations, so you can, that when you will need this. Okay, so yeah, so we have this next theorem, which I don't know the pronunciation. I think it's Nagel's, but I'll just call it the Na theorem, because I don't know. I couldn't find the pronunciation of it. So this
Nagel
Na
only.
theorem states, yes, sir,
Nagel.
Nagel. Okay, so Nagel's theorem just says that if t is equal to x comma y is a rational point of finite order, then x and y are integers, and either y is equal to 0 or y squared divides d, and d is just the discriminant. So now we have this really nice thing, right? So we were worrying about torsion earlier, and it turns out that every element of torsion has to be an integer point. Okay, that's what Nagel's theorem tells us. So yeah, so, and this, if you think about it, this actually gives us a way to find all elements of the torsion. Can you think of why, like, they would, why why we can, how we can get the torsion element from this? Because we have like the possibilities, right? D is going to be some finite integer, so we can find all integers y such that y squared divides d, and then we can find if for that y is x going to be an integer as well, and if x is also an integer, then x comma y is an integer. So it might be possible that x comma y has a finite order. Is this clear? Like, even intuitively a little bit?
Yes, proceed.
Okay, so either y is equal to 0 or y squared divides d. Okay, so the inverse of Nagel's theorem is not true, and need not be true, and that basically means that if you have an integer point on the curve, it is not necessary that that the order would be finite. So you have to check for every point, integer point that you get using the Nagel's theorem, you have to check if that has a finite order or not. But you might be wondering how we can check if it has a finite order, right? We would have to keep adding it, and maybe the order is like 1,000 or 2,000. And it can get arbitrarily big, right? Integers can get arbitrarily big. So we don't know what the order would be. So we need something for this. We need another theorem which can put somehow a limit on how big the order can be, and that's what Mazur's theorem is. And the Nagel's theorem is the proof of Nagel's theorem is easier, but Mazur's theorem is really difficult to prove. And it basically states that if some point P on E has finite order n, then the order is either between 1 and 10 or it's 12. And now we have all the theorems that we need to figure out what point would have a finite order. So basically you use Nagel's theorem to find some integer points that could be of finite order, and then you use Mazur's theorem to check all the cases 1 to 10 and 12. And if at any point you get the identity, then that means that point has finite order. So just try to use these. Don't try to look at the proof or anything. Just try to use these to find torsion subgroup of some examples. So I'll give you two examples. So y squared is equal to x cubed plus x. You can check by differentiating it with respect to x and y that it's an elliptic curve. It has no singular points. So the group law is true. If the group law is true, we can use all these theorems. And also we're working with rationals, so the discriminant is just this because we have reduced it, because this is the reduced form. And you can try to find the torsion of this. Similarly, you can also find the torsion of this. So yeah, that is just an exercise. Okay. So I'll stop now.
Very good, actually. Excellent. But of course, so we need to know certain details. Some people, some students may be not aware of connecting things, for example, immediately. Okay, so it may take time. We'll try to connect it later again. So there is a book called Rational Point and Elliptic Curves by Silverman and Tate, right?
Yes.
So that is a very good book, and there are some elementary books also. AMS, American Mathematical Society, published for student versions. So one can look into them, and yeah. So later we'll try to. Me and Lalit will come forward again at some other point of time. So we may try to give some series of talks. We'll go in little depth now. At least some of you got an idea that what are these. So please read. And at that moment, you also come to help us, so that each one of us will take up a little portion. So for example, one of you take this initial part, right? Me and Lalit take will some other parts. So maybe I'm just saying that we need to have some aims, right? So let us have some aim. In future, again, we'll take some 3 talks continuously or like that. Some holidays time we can offer. Okay, we'll plan it. Yeah. So because I'm saying you 3 people, but actually now we'll post this video. Many other people can watch it. They will also come forward. So it is for everyone. Okay, thanks for this wonderful talk. So we'll stop. I'm stop sharing now.